Welcome back. We now start with this theorem. Let's let G be a group, and uh, uh, and I'm going to assume that the notation for the group operation here is multiplication. That's the default. So we always use multiplication as the default group operation in theorems and proofs. Let's let A be an element of G. If A has infinite order, then A to the I is equal to A to the J if and only if I and J are the same. So put differently, what we are saying is that if A has infinite order, then all powers of A are distinct. And so the subgroup generated by A is the set of all powers of A to the k, where k is an integer, and where A to the I is not the same as A to the j for I not equal to j. So this is pretty much telling us that the powers of A are all distinct. Let's try to prove this. If it were the case that A to the I and A to the j are equal for some I greater than j, that is, if it were the case that A to the I is equal to A to the j for some I and for some I not equal to j, if I and j are not equal, then I can assume that one of them is bigger than the other. So that's why I'm saying, so here I'm saying what we're trying to prove here is that A to the I is equal to A to the j if and only if I and j are the same. So I'm kind of assuming the opposite, and I'm going to get a contradiction. So if it were the case that A to the I and A to the j are equal for some I not equal to j and I bigger than j, then clearly if I multiply both sides of this equation by A to the negative I, that's the inverse of, if I multiply both sides by the inverse of A to the j, that is A to the minus j, then I'm going to get A to the I minus j is equal to the identity. And since I minus j is positive, that this contradicts the assumption that A has infinite order. So remember, A has infinite order means that no power of A, no positive power of A is equal to the identity. So if you recall the definition of infinite order, it means that no positive power of A is equal to the identity. So here, if I assume that A to the I and A to the j are equal for some I greater than j, then I see that some positive power of A is the identity, which contradicts the assumption that A has infinite order. So this is it. So that's the proof of the theorem. Okay, so the next theorem here, let's let G be a group and A be an element of G, and assume that A has order n. So remember the meaning of this, right? A has order n means that n is the least positive integer power of A that is equal to the identity. So n is the least positive power of A that's equal to the identity. So that's the assumption. And what we are claiming now is that if A to the k is the identity, then n, the order of A, divides k. So if the kth power of A is the identity, then k is divisible by the order of A. Let's try to prove this too. Let's notice that, let's assume that A to the k is the identity. And by applying the division algorithm, we can express k so if as nq plus r, where r is greater than or equal to 0 and less than n. That is, that is, we are dividing k by n, and then we are getting a quotient and a remainder. Okay, then what is a to the r? Well, a to the r, so if you solve for r here, you get r is equal to k minus nq. So a to the r is equal to a to the k minus nq. Now that we can rewrite as a to the k multiplied by a to the n to the negative q by using laws of exponents. And by assumption, a to the k is the identity, and also n is the order of a, so a to the n is the identity. So a to the n is the identity, a to the k is the identity, so the whole thing here would be identity. So what we see then is that a to the r is equal to the identity. But wait a minute, n is the least positive integer such that a to the n is the identity, and r is even smaller than n, and a to the r is the identity. So we must have that r is 0. But if r is 0, then k is a multiple of n. So we get that k is nq, and n, which is equal to the order of a, divides k. And that completes the proof of this theorem. Okay, so I'm going to stop the video here, and in the next video we will be looking at another theorem.